Good morning, everyone. So let's start today's session. In previous session, we learned about the Biot-Savart law, the basic principle or the expression behind the derivation, right? It's the expression behind derivation of magnetic flux density around some current carrying standard current carrying conductor. Like we learned how to find the magnetic flux density around infinite long straight current wire and a circular loop, current carrying loop, and a solenoid like this, right? Right. So today we'll focus about the what happens if there are two parallel current carrying conductors, right? Kept close together, right? So let's see what happens there. So force between two parallel conductors carrying current. Here, so let's consider two parallelly placed current carrying conductors, right? So actually we can have two ways of current carrying conductors, of two current carrying conductors uh, parallelly like this. So one way is to have two infinitely long current carrying conductors which transmit current in same direction. Let's say upward, I1 and I2. And the other way is two parallelly placed current carrying conductors, but transmitting current in opposite way. I1, now this is upward, this is the other one. Let's say it is now current is flowing down, I2. Right? So we know from the uh, right hand rule, when our thumb is pointed towards the direction of the current, the other four fingers would give the direction of the magnetic field. So around this I1, there would form a magnetic field like this around it. There would form a magnetic field around it. And around the second current carrying conductors, they would form a anti-clockwise magnetic field around the current carrying conductor. Hmm. Right? So around these two, it would be like this. Around I1, there would be a magnetic field in the anti-clockwise direction. And around I2, there would be a magnetic field now in clockwise direction. So here we can clearly see if we get this middle region between the two conductors. Here, according to this first figure, they get cancelled out, right? Because these blue lines are upward and these green lines are downward. So the magnetic field, these two, the magnetic field would get cancelled out because they are opposite in direction, right? So, but if we consider either this region or this region, here blue color magnetic field is downward as well as. So although I have not drawn all the magnetic field line, there are magnetic field lines which is distributed to infinity, right? Not only there are no. This doesn't mean there are only two magnetic field lines, right? To have a clear picture, I have not drawn all the magnetic field lines. So around this second wire, there would be magnetic field like this, infinitely distributed. So you can see, if we consider this region, there are blue lines coming downward as well as green lines coming downward. So here magnetic field would be added up, right? Here also blue lines going upward and green lines going upward. So magnetic field would be added up there as well. So if we draw the resultant magnetic field, superposition of superposition of two separate magnetic fields, right? Two separate magnetic field. Let's again draw the two I1 I2. The resultant magnetic field would be like this. So middle part, as you can see, the magnetic fields get cancelled out. So there are no magnetic field in the middle part. At zero magnetic field. And if you go to the left, they would get added. There would be a magnetic field like this. Middle region, the magnetic field would be less. Here also same. They would produce a magnetic field like this. Right. So you can see now this middle region is having a lack of magnetic field or less amount of magnetic field than the two other regions. So due to that, there would occur, right? There would induce a force So less magnetic field. This region, weaker magnetic field. Magnetic field due to the cancellation of the two magnetic fields. The resultant is weaker magnetic field, right? Yeah, if you consider these two regions, it is a strong magnetic field. Right? Strong magnetic field. Middle it is a weaker magnetic field. The two sides is strong magnetic. Then what would happen? Right? Since this middle magnetic field is weaker than the two sides, there would occur a force, magnetic force, which attracts the two conductors, two current carrying conductors towards each other. Attraction force. Same attraction force. Right. So likewise, if we consider the other two, here what happens? The current carrying, so these in same reaction. I1, I2. Now here the middle part is get added up. Middle part, and we you can say the middle part, the two magnetic field get added up. So there would be a strong magnetic field. In the middle part, middle region, and if we consider, let's say this left hand, the blue color lines are downward and green color lines are upward, so they get cancelled out. We consider this region, blue color lines are upward, green color lines are downward, they get cancelled out. So weaker magnetic field. On the two sides and middle, it will be a very strong magnetic field. Then we can draw something like this. Middle it is strong. On two end is weaker. Right. So middle it is very strong, the magnetic field. There are magnetic lines close together, right? Here, a strong magnetic field. The two ends, weaker magnetic field. Weaker. Right? Weaker magnetic field. Then as a result of that, what would happen? So middle it is stronger. on the two ends, it is weaker. So there would occur repulsive force, repulsive magnetic forces on the two conductors. So the final conclusion we can have, if there are two current conductors parallelly stationed, which transmit current in same direction, they get attracted. Whereas if there are two current carrying conductors stationed close together, but the direction of current is different, then what happens? They get attracted. They occur repulsive force, right? Repulsive force would be there. So that's the final conclusion that he can make. So if there are two parallel current carrying conductors, two parallel current carrying conductors, two parallel current carrying conductors through which current transmit in same direction. Cross same direction. The two conductors are attracted. The two conductors are attracted together. Together due to the induced magnetic field. Due to a magnetic field. If there are two parallel current carrying conductors through which the current flows in opposite direction, they occur a repulsive force. And so if there are current carrying conductors through which current flow in opposite direction. Other two conductors are repulsed. Survey due to a magnetic force. Force. due to magnetic force. So here we can easily find this mutual magnetic force between the two conductors, whether it be repulsive or attraction forces. And next one is finding the mutual magnetic force. Right. So if let's say they are r distance apart, if two conductors are r distance apart, right? R distance. They are r distance apart. If they are distance apart, I can write the magnetic field acting on the first conductor due to the second one. Let's say magnetic field acting on first conductor, due to the second one. On first conductor due to second one. Right. So I'm considering the magnetic field acting on this due to the second one. Right. So we can see it is using the right hand spoke rule. It is a magnetic field coming outward. Second one, they be mu naught I2 over 2 pi r, 2 pi r. So this is the magnetic field due to second current carrying conductor. Then the force. So here you can see magnetic field is induced magnetic field on the first conductor. The second one is outward. Outward. Outward from the whiteboard. And using the Fleming right hand rule, left hand rule, we can see from the Fleming left hand rule. Right, so the point the index finger in the direction out from the whiteboard and current upward direction. Then your thumb will be pointed towards right. So we get the same direction of magnetic force acting in the current carrying conductor if we consider the Fleming left hand rule as well. And from the Fleming left hand rule also we have this direction of right. So here we conclude the direction of the Right, so here we conclude the direction of this magnetic force by considering the resultant magnetic field. But without doing that, we can find the direction of the magnetic force using the left-hand rule as well. Right, using left-hand rule, because here the magnetic field acting on the first conductor due to second one is out from the whiteboard. So point the index finger in that direction, then the middle finger in the direction of current, which is upward, then thumb would be eventually pointed towards right. It's the same direction of the magnetic field. Then here, the force. Let's say if the length of L is considered on first conductor, magnetic field, magnetic force acting on the first conductor and magnetic force acting on the first conductor is, let's say, if one is V2 I1 L. Because here we are considering the magnetic field acting on the first conductor. So the magnetic force and the magnetic field is acting on the first conductor due to second conductor V2, and the current through the first conductor is I1 L. So V2 is from mu naught I1 2 phi R. I2 is I2 I1 L. And so this is the expression. So in similar manner, right? In similar manner, if we consider the magnetic field acting on the magnetic force acting on the second conductor, we get the same expression. In similar manner, magnetic force, right, acting on the second conductor F2 same, not I1 I2 L over 2 phi R. Same. Right, so we can say this is the mutual force, mutual magnetic force acting on the two current carrying conductors. So the direction we have to by either using the left-hand rule or by considering the resultant magnetic field acting resulting magnetic field due to the two separate magnetic field, we can find the direction of this magnetic force. Therefore, mutual magnetic force on two parallelly placed conductors F is U naught I1 I2 L over 2 phi R. Over 2 phi R. Then magnetic force acting on a unit length is just by dividing. You can apply magnetic force acting on a F4L to phi R. Right, so this is the expression for the mutual magnetic field acting in between two current carrying conductors. Two parallel placed current carrying conductors. Right, so then actually we can use this to find a definition for ampere. So, no definition for ampere. Right, not. Definition for ampere. The unit, the ampere is the unit I used to find the, used to define the current, right? Definition for ampere. If two parallelly placed conductors parallelly placed, if two parallelly placed infinitely parallelly placed straight conductors two parallelly placed straight conductors 1 meter apart, each carrying 1 amperes of current. 1 ampere of current. That 1 ampere of current. We can write OL is mu naught 1 into 1 divided by 5 into 1. So mu naught over 4 5 into 2. So 4 5 is 2 is 10 to the power minus 7. Newton. Actually, the definition is if the magnetic force acting on a unit length is 2 × 10⁻⁷ Newton for two current carrying conductors, two straight current carrying conductors which are 1 meter apart, then The current flowing through each conductor is 1 ampere. That's the definition, right? So if force acting, if magnetic force that's a magnetic force acting on unit length of 2, acting on unit length of 2 parallelly placed straight current carrying conductors straight current carrying conductors current carrying conductors of 1 meter apart, right? Of 1 meter apart. The current through each conductor will be 1 ampere. Is 2 10 to the power minus 7 Newton per meter. And the current through each conductor is 1 ampere. The current through each conductor is 1 ampere. This is the definition for ampere using this mutual magnetic field acting on 2 current carrying conductors. Right, now let's see some questions. So here, first question, the two straight wires ABCD carrying equal current are placed symmetrically and at right angles to each other as shown in the figure. AB is infinite long and CD has small, right length. The magnetic effect on CD due to AB gives rise to, so they are asking about the magnetic force acting on CD due to AB. Right, so using the right hand clock rule on AB, here the magnetic field acting on this side is into the whiteboard. Right, but this side is out from the, because there's a magnetic field in clockwise anti-clockwise direction around AB. So because the right side it is into the whiteboard, right, left side out from the whiteboard. Then if we consider length like this, easily using right hand can find. So point the direction of the magnetic field and middle finger in direction of current, there would occur a magnetic force upward. And if we consider same segment on the left side of the conductor, and there would occur a magnetic force downward of same, I'm considering same delta L length. Same delta L length. Same delta L length. And likewise, if you consider these 2 points, these 2 line segment, at same kind of thing happen. Okay. So you can see now, so result there is the resultant force. No, right? Because this force get cancelled out this one, this force get cancelled out this one. So to blue color force cancel out, to green color force cancel out. There is no any resultant force, but there would be a force coupled in anti-clockwise direction. So due to this, what happens? Due to the AB, there would be zero resultant force, but anti-clockwise coupled. All these forces get cancelled out, having zero resultant force, but there would be anti-clockwise coupled. Both one is the answer. Right, so here 2 long parallel wires placed normal to the plane of paper carry equal current in opposite direction as shown in the figure. The variation of the component of the magnetic flux density in y direction be along the x-axis is represented by. Right, so due to this F1, there will be a so there would be a right, so let's draw it again. Due to the left conductor, there would be a so you can use the right hand stroke. There would be a magnetic field pointed upward direction. Like this. Because the right side, there would be a point magnetic field upward direction, but decaying. Because the left side to be like this. Right. Then consider the other conductor. Right. Point the thumb inward the whiteboard. Then there would be. So I'm considering this upside as positive. Side as positive. Right. So there would be a magnetic field in upward direction here. Right, due to the first conductor, that's why it is considered as positive. Here it is negative, other direction. At the upward direction, so it is positive, negative. So the resultant of these two would be something like this. Resultant magnetic field. Something like this to be red color. So the second one. Next one, a thin uniform wire PQ current of pi could be held without any mechanical support. Power and pi along horizontally via RS carry the same current I. If the mass per unit length of the wire PQ is M, the equilibrium height of H. EQ of RS is given. Right, so first you have to identify the direction of magnetic field acting on PQ. The direction of magnetic field acting on PQ due to RS. Current is towards right. There would be magnetic field from the right. In using left hand rule, find the direction of magnetic force acting on PQ. Right, so I point the index being the direction of the magnetic field, middle being in the direction of current, then we would have force upward. Right? FB. This magnetic field on PQ, this magnetic field, let's say B. This B is actually, you can find it is mu naught I over 2 phi H. So the previous knowledge, the magnetic field around infinite long straight current carrying conductor mu naught I 2 phi H is the distance. The point is considered. Then consider the PQ. Very easy. PQ. Say L is the length of the PQ conductor. Is the force is weight acts downward. Weight is M Lg. Right? M is the mass vector and is the length of the conductor into G. So they are equal. Right? They should be equal. To have to be inequal, they should be equal, right? Right. So FB is B I L M L G. L get cancelled out. B is we found mu naught I 2 phi RH. I mg. Then H is mu naught I square 2 phi mg. 2 phi mg. Then third one is the answer. I square. Here, an infinitely long thin straight wire held perpendicular to the plane of the paper at point O. Current I into the paper as shown in the figure. 9 other similar infinite long wires. Infinite long wires parallel to the above wire and held on the circumference of a circular radius R with center at top. It carries a current I into the paper, except for wire A and B. The angle separation between two consecutive wires is 30, as shown in the figure. The magnitude of and the direction of the magnetic force per unit length of the wire held at center of the wire is. Here, first we have to consider these two wires. For example, the distance is same between these two wires and these two wires. So there would occur a force attraction, or same attraction force with same magnitude but opposite direction, so they get cancelled out. So same thing happens to these two conductors. Same thing happens to these two conductors. Only the resultant force would be due to these three conductors. Resultant force would be only due to these three conductors. Degree. So they would occur same force F. This distances are same or F. The resultant force is upward F plus 2F cos 30. F plus 2F cos 30. F 1 plus cos 30 is root 3 over 2. So F 1 plus root 3. F, we can find it. It is mu naught I squared 2 by R 1 plus root 2. What direction? Second law. The answer, right? Right. So let's move on to the next section, which is you're going to find the torque acting current loop. And so which is very useful actually. This next section. Uh, this is the basic governing mechanism of moving coil galvanometer as well as a DC motor, right? It will be how this galvanometer and the DC motor works, right? That is totally with the torque acting on current loop, right? Now let's look at this one. So consider a current loop, right? So consider a rectangle current loop, right? Consider a rectangular current loop having n turns, right? N turns of height A and breadth B. Breadth B, which is positioned in a magnetic field. So this is the current carry loop that we are considering. I and this is field rotate, yeah? Field rotate around this axis. Right, so there is a magnetic field. Right, so there is a magnetic field acting in this direction. B. Right? It is not the PQRS. It is not parallel to QR side. It's magnetic field. Right? Then using the Fleming's left-hand rule, right? Fleming's left-hand rule, we can find. Right? So we can find that. Consider the QR side. We consider QR segment of this loop. QR segment of this loop. Using Fleming's left-hand rule, we can find that there would occur magnetic force down F. So dash. And if we consider this PS segment, there would occur same magnetic force upward F dash. So these two get cancelled out. So although there is a magnetic force acting on QR and PS segment of this loop, they are opposite in direction and same in magnitude, they get cancelled out. But then let's consider RS segment. Because it is RS segment and apply this left hand rule. So what is the direction of the magnetic field? So there would be a magnetic field this direction, current downward, right? And there would occur the current downward. Magnetic field, magnetic force in this direction. Here also, opposite direction. 90 degrees angle. That's what magnetic field is in this direction. Like this. Height is A. Breadth breadth is B. Breadth is B. Breadth is B. Then this F can be found using FBI, BIL. And so magnetic here as it is shown in the above figure. The magnetic force acting on QR and PS segment. The magnetic force acting on QR and PI segments. Are same in magnitude and opposite in direction as well as in line. In line. So they get cancelled out. They are in line. Resulting no resultant force or couple. Force couple. But if we consider the Q, PQ and RSI, PQ and RSI, and RS segments are considered. Segments are considered. They are occur they are occur magnetic forces. Which are opposite in direction but not in line. Which are same in magnitude, opposite direction but not in line. Same in magnitude. Which are same in magnitude. Not opposite direction. Magnitude and opposite in direction. Same in magnitude and opposite in direction. But not in line. Therefore, whatever. Therefore, since they are not in line, they occur a force couple. Therefore, there would be a force couple. Force couple acting on the loop. On the loop, making it rotate on the loop, making it rotate around the axis in clockwise direction. Right. So this stroke we can find So if I look from above, that's what, how would I see? So this theta or something, theta. Somewhat here, right? Perpendicular, to be perpendicular to that. And so if I look from above, from above, so this B this is how the two forces would act. And so F could be found. But here F is B I A. That A is the length of the conduct, this PQ segment A. And since there are now n number of loops, n, and multiply by n, BIAN. Then here the torque is F into B cos theta. Right, so this is active direction of the magnetic field. BIAN into B cos theta. Torque BINA into B cos theta. Here A into B is A. Right, A into B is A. Is the cross-sectional area of the cross-sectional area within the loop. Right, the area of the loop. So here you can see the torque if BI, all the other parameters are kept constant, the torque acting in the loop is proportional to the area of the loop. So if somehow this magnetic field is made parallel to the B segment, they have to occur the maximum torque, right? QR segment. If magnetic field is made parallel to QR segment, magnetic field is made parallel to QR segment, the torque, the magnetic field is made parallel to QR segments, the torque becomes maximum. Is theta is equal 0, parallel theta. Sim torque is BI NA. V is the magnetic field density, magnetic flux density. I is the current through the loop, N is the number of turns, A is the process, A is the area of the loop, area inside the loop. N is the number of turns. A is the cross section area inside the loop. Right, so this is the torque acting in a current carrying loop. Right. Right. So moving coil galvanometer is is based on uh, this current carrying loop. Right, this kind of loop. Right, this rectangular loop, as you can see here, this is the rectangular loop. This is that loop. Hmm. So this is that loop. So how to have the maximum torque here, to have the maximum torque, the magnetic field should be made parallel to QR side. So how can it be attained? Right. So here you can see here cylindrical magnetic poles are used. That's when cylindrical magnetic poles are used like this. North, south. Cylindrical magnetic poles are being used. So this is the core. Right. So this loop, current carrying loop is attached to a soft iron core cylinder, right? So this is the loop. Here the specialty here is this magnetic field act like this. Right, not straight magnetic field is somewhat the cylindrical shape of the magnetic poles. due to cylindrical magnetic pole, the magnetic field acting. So magnetic field is always parallel to this conductor. So there would occur the maximum torque. Right. So due to due to the shape of the cylindrical pole, cylindrical magnetic pole, there would occur a radial magnetic field. So that always magnetic field is parallel to the top side. Right. So magnetic field parallel to the top side of the loop. Loop making the maximum torque. Right. So top of the loop always resulting maximum torque. So here you can see current goes up. This is the force. These are the two forces acting on this loop. They are perpendicular to the top side. So maximum torque would generate, right? Always the maximum due to this cylindrical magnetic pole, always the maximum torque could be generated. Maximum. That's a point of having the cylindrical shape magnetic poles. Right. And here you can see there is hair springs, right? So now that you know when current is allowed to flow through this current loop, there would occur force, right? There would occur a force couple, which results to rotate this uh, loop, right? Current loop. But in order to resist that, as a resistive force, there is a hairspring. There is a hairspring attached to resist this loop. I mean, if there is no any hairspring, then this would continuously be rotated. If current is allowed to flow through this leaf, this will continuously rotate. Actually, that's what happens in the DC. But here, right, so after some point, this point should stop, right? So point should stop. So therefore, in order to stop this force couple, right, torque acting on the loop due to the current flowing through the loop, there should be a resistive torque acting in the opposite direction. Right? So to counter the torque acting on this current carrying loop, to counter the torque acting on the current carrying loop, there is a hairspring attached to the galvanometer, which generates a counter torque. Counter torque, it generates a counter torque. Counter torque to the magnetic torque. Counter actually mechanical torque. The magnetic torque. Let's say now so let's say when the equilibrium is attained. So when let's say after allowing the current flow through this current carrying loop, the pointer pointed towards here, then the angle is theta. The deviation angle of deviation is theta. Right. So if the spring torque constant is C, the spring torque constant is C, and after coming to equilibrium, the spring torque constant is C, and after coming to equilibrium, the angle of is theta, right? Then after coming to equilibrium means the mechanical torque should be equal to the magnetic torque. is equal to mechanical torque. So magnetic torque is BI NA, right? So here the maximum magnetic torque is applied. Right? BI NA. Mechanical torque is mechanical constant into theta. So here if I is subjected, I is C or B N A theta. So C is a constant, B is a constant, N is constant number of turns, A is a constant. So I is proportional to theta, right? Here, since C, B, N, and A are constant, I is proportional to theta. Theta is the angle of deflection. Angle of deflection, right? Angle of deflection. So here, now it is clear that current flowing through the galvanometer is proportional to the angle of deflection. Current flowing through the galvanometer is proportional to the angle of deflection. Therefore, this galvanometer could be used to measure current as well as can be modified to measure voltage as well. It's clear that galvanometer could be used to measure current as well as could be modified to measure voltage. That we will discuss in the current electricity part, right? So this same galvanometer could be used to. So we can see here, current can be, small amount of current can be measured directly, milliampere range. But this can be modified to measure the current in ampere range as well as to measure voltage, and this could be used to measure the ohm resistance Resistance of resistor. Only could galvanometer only could be directly used without any modification to measure milliampere ranges. Measure current directly used to measure current in range of milliampere. Right? If this is directly exposed to ampere range, then this would burn up. Right. Next one is sensitivity of the galvanometer. sensitivity of the galvanometer. Sensitivity is the amount of deflection per unit change in current. Theta y is the amount of deflection per unit change in current through the theta y. And from the second, theta y is BNA or C. Right, so the sensitivity is. So sensitivity of the galvanometer can be increased by either increasing the magnetic field or the number of turns and decreasing the torque constant on the hairspring. Can be increased by increasing the increasing increasing the magnetic field, increasing the magnetic field or the number of turns of the loop and by decreasing the torque constant of the hairspring. Right. Then the last apparatus, which is governed by say the same principle, the torque acting on a current carrying is the DC motor, the basic DC motor. Here the components are this called the current carrying loop is called the armature of the motor, and this is called the commutator. Right, so here what happens? There are two magnets. The armature picture. So armature is connected to commutator. And so if there is north pole, south pole, so there is a magnetic field in this direction, current flow in this direction. So this is will rotate around this axis, this loop. What is the direction of physical rectangle? So what is the direction of the force? The current flow in this direction. Magnetic field is force is magnetic force is what? Out. Right. Then again, now this is rotate in anti-clockwise manner. This loop. The purpose of this commutator is, right? What is the purpose of this commutator? So this is to so this commutator is also rotates with the loop. Commutator also rotates. Right. So this commutator then the after rotation, say a half of the rotation. Let's say due to this torque, this halfway rotated. halfway rotate. Somewhere here. Loop is now like in this manner. Pause. F, F. And so after being rotated, after rotating a complete cycle, so you can see this commutator get interchanged. Right? Commutator get interchanged, and the current direction would be in same direction. Since the commutator also rotates the loop after 180 rotation, the two sides the commutator gets interchanged, allowing current to flow through the loop flow through the loop in same manner, same direction. In same direction. Same direction. Same direction. So that the applied torque is also same thing. Same sensation, making the loop to rotate in same direction continuously. Continuously rotating the same direction continuously. So that's how the DC motor works. By interchanging direction of the battery, battery direction of the rotation can be changed. Right, so that's how the DC motor works. The applied torque rotates the uh, loop. Rotates the loop. Now let's try some questions. Here it is said a rectangle coil of length 0.1 meter and breadth length a meter, breadth consists of 500 tons. Then uniform magnetic field of flux density Tesla well carries a current of this much. Current is 10 to the power minus 2 ampere. Possible torque on the coil is maximum possible torque. Right, so maximum possible torque in A 0.1 I 10 to the power minus 2 N 500 A 0.04. So it comes 2 in 10 to the power minus 2 minus 3 Newton meter. Second one. Next question, a figure shows a cylindrical satellite with radius r, length L, wire PQR wrapped around it in a rectangle shape. The current I is made to flow through PQR is an instant when the direction of the magnetic field of flux B is along PQ. Along PQ, this direction is the magnetic field. What happens? And so we know there would occur force coupled in this direction. So now these two forces get cancelled out. If dash, they get cancelled out. There will be a force coupled. People is F. And so net force will be zero. There will be no net force, but torque. No net force. But a torque is F into R. F is B IL, simple I L into 2R. So 2R L I V of torque will be X. So there will be no net force, but torque of 2R L I V electron satellite, which would rotate satellite in anti-clockwise direction. Here, each of the single turn wire loop placed on XY plane as shown in the figure carries the same current I. Uniform magnetic field is applied along the positive direction of x-axis, uniform magnetic field. Yes, x-axis. Assume that each wire loop rotates freely about its symmetrical axis perpendicular to the magnetic field, which of the choice represents out of the loop that initial torque acting on the adjacent. So torque is BINA. If BIN, all those are constant, And so it is given at same current flow and having one loop, uniform magnetic field. Each while loop rotates field about symmetrical perpendicular magnet, which represent the loop that the acting singleton wires. N is same, I is same, B is same. Right? So since B, I, N are same, torque is proportional to the initial torque. So the highest initial torque would be required by the loop having the highest area. Right? So we have to find the area here. Here area is this one, half into 2 into 3, which is 3. Right? The area of P. Area of P is half into half is area of the second one, Q. Is 1 into 4. Area of the next one, EQ, R. Pi R squared, so R is 1.5. Around 7. In the area of the last loop, S is 1.5 square. 2.25. That's all. Area, highest area is AR, then AQ, AP, AS. So torque is also proportional, same manner. So highest torque will be for R, then for Q, then for P, then for S. So RQPS is the descending one, torque. Second one. Right, so that's basically the theory part, or the theory part related to this magnetic field section. So here First, we learned about there are two types of magnet, permanent and induced magnet. And, from the magnetic, studied about the magnetic force acting on conductor, current carrying conductor. Then the variation of the distribution of magnetic field around some standard magnet like Gauss magnet, bar magnet, and also around current carrying conductors. So you see right hand screw rule, this direction of magnetic field can be found. And then you then learned about the left hand rule to identify the relation between magnetic force, magnetic field, and current, which are perpendicular to each other. And then learned about the force acting on a current, force acting on a moving charge, then PQV. Then about the Hall effect. But, then finally, the Biot-Savart law, the basic law behind the derivation of the expressions for the magnetic flux density of current carrying conductors. Right? Then we learned about the the equation, the expression for the magnetic flux density surrounding finite straight current carrying conductor and circular shape loop as well as solenoid. Right, so finally about the mutual force acting between two current carrying conductors, straight current carrying conductors. Finally, the torque acting on a current loop, which is the basic governing mechanism behind the galvanometer and the DC motor. And so that is all about this magnetic field. And thank you.